Alright, hello and welcome back to our proofs slides. So, if I remember correctly, we stopped, oh, I passed it. We stopped here, and so maybe I'll just recap this and then we'll go on to prove for alls, or think about them in a new way. Alright, so we have theorems, and those are just things that you can prove, right? So, a theorem that we're going to prove later is that the square root of 2 is irrational. So that's whatever you want to prove, you can call it a theorem if it's special enough, okay? And to prove one, you can use all of your weapons that I am teaching you. So you've got logic so far, and you can make plenty of assumptions in the form of axioms or just things that you assume to be correct in the proof statement. And I think this is the key. This thing in bold right here is what I want you to think about when you're proving something. So every time you prove something, it's always, you have some conclusion that you're making, and you have a bunch of things that you're assuming to get there, okay? It's like under the assumption that, I don't know, grass is purple, pigs can fly. That's actually a true theorem, all right? Because of the assumption was wrong. So get your assumptions correct. That's also useful to remember to do. And you can also use all your previous theorems because you're just building up a corpus of knowledge that you can then throw at whatever you're trying to prove later. Okay, so that's how proofs work in a sense, and so we're going to get some good practice in this set of slides. So let's go back to proving for all. Okay, we remember the slides from last time where it was saying something like, okay, assume, I don't know, some element A in the domain is arbitrary, and then prove P of A, then you have shown that for all A, P of A is true. Okay, so that's one way to prove it for all, but there's others. So here are your examples. Here are your options. So the first thing that you can do, the easiest thing that you can do probably to prove a for all quantified statement is just try every element of the domain if it's small and finite. Okay, it's like, okay, everything between 2 and 5, every element x between 2 and 5 inclusive has this property. Okay, that is super easy to prove. You just try them all and you have a for all out of that. Okay, that's easy. And then the one that we know already, it's called universal generalization. Okay, that's the name of the rule. And so you just prove your conclusion, the rest of the statement, prove that it's true for an arbitrary element, and then you suddenly have for all A, P of A. All right, we'll get examples of that. And then remember that if you want to prove the opposite, if you want to prove that a for all quantified statement, like for all x, P of x, is false, remember that that is equivalent to there exists an x such that not P of x is true. Okay, so you kind of just bring it in and flip that. Okay, so the way that you prove it in English is you say you provide what's known as a counterexample. So if you're trying to tell me that it's not true that all these things have this property, then there must exist one that doesn't have it. Yeah? That's the idea. So this is just that in English. And the one thing that you find that doesn't have that property, P of x, is called your counterexample. Okay? It ruins the whole show. It rains on your parade. Okay, that's called a counterexample. It's showing that it can't be true that for all x, P of x. Right? So that is how you prove a for all. And before we get some examples, I'm going to have you try it yourself. Let's talk about proof etiquette. Okay? Maybe I should say that here too. All right, so when you're writing a proof, and you'll see this in the book, it's customary to start that proof by saying proof in bold with a period after it. It's like, all right, hello, here's my proof, begin proof. That's the idea there. And after you're done proving something, you worked so hard, all the mathematicians, we like to brag about what we just did, and we essentially give a mic drop at the end of our proof, okay? So the way that you give your mic drop is to put either a rectangle or you say QED. Okay, those are your two options that are standard to do, and most people like the rectangle. QED stands for, I mean this also stands for QED, but QED itself stands for the Latin phrase quod erat demonstrandum, which means which was to be demonstrated. Okay, so it's essentially saying that, hey, whatever I was trying to prove, I just proved it. Look at me. All right, so that is how you structure a proof. And so now I'm going to ask you to write one. Okay, so I want you to prove the following statement using a proof by exhaustion. So take a look at the statement, and I'll read it out in English too after you've given your own shot at it. And first, you should definitely try and convert this to heavy math, because it makes it easier sometimes to prove things. So give this a shot, convert this statement to math, and then use a proof by exhaustion to prove that this is a true theorem. Okay? You are ready. Give it a shot. All right, assuming you're back with me now, let's do this. So let's convert this to math, first of all. This is equivalent to saying for every integer n, for all n, such that 0 is less than or equal to n is less than or equal to 3. So only if this is true, we want to prove that this is true. Okay, so that's how you can read it, and there's an implication involved. It's hidden there. That implies that n plus 1 squared is greater than n to the power of 3. Okay, so that is your math statement, and now we're going to go and prove this. We say proof, and usually you sometimes say like how you're going to prove it, so by exhaustion. And so, well, you only got the following elements. We need to show p. Let's call this p of n. Let's see. Or no, let's call not the whole thing, but the inner part. Let's call this p of n. So I need to show, to prove this theorem by exhaustion, that it's true for all these n that respect this this inequality. So I need to prove it for p of 0, for p of 1, for p of 2, and not p of 3, because we're not going that far. All right, so that's all I need to do. And once I've done that, I've proved the theorem. Okay, are you ready? Let's go. So p of 0, what's p of 0? And I'll just do this fast. You can imagine how you can write the rest of this out. P of 0 is saying that, let's write it up here maybe. This is part of our scratch work. P of 0 is saying that, okay, n plus 1, n is 0 in this case, because this is p of n. So 0 plus 1 squared, so 1 squared is greater than 1 cubed. Dun dun dun. No, sorry. Is greater than 0 cubed. Excuse me. That's the idea. And that is totally true, because 1 is greater than 0. Yes, that checks out. Dun dun dun. So, p of 0, because 1 squared is greater than 1 squared, which is equal to 1, is greater than 0 cubed, which is equal to 0. Okay. And then you can do the same for P1 and P2. I won't do both of them because I don't know if that's not a waste of time or not. Maybe I will. Okay, P of 1 is saying that 1 plus 2 squared is greater than, 1 plus 1 squared is greater than 1 cubed. So 2 squared is greater than 1 cubed, and that is totally correct because it's saying something like 4 is greater than 1, and that totally checks out by math. P of 2 is saying that, let's see here, 2 plus 1 squared, so 3 squared, is greater than n to the cubed. Whee. So n cubed, that is, greater than 2 cubed. Sorry, it's hard to keep all these numbers straight, but I hope you're following me. And this is true because this is equal to 9, and this is equal to 8. Okay, so I have proven all of those, and that is what I needed to show to prove this theorem. Mic drop. We're done. Okay, I hope that that wasn't too bad, because this will be your life for this chapter's homework. Okay, so that was our first proof. Okay, time for the next example. This is another one that I want you to try, so give a counterexample to the statement below to show that it's false, because this is a for all kind of statement. So let's make it math together, and then I'll let you go off and try it yourself. Saying, all right, if n is an integer, this is a for all. So n is an integer, and n squared is divisible by 4. Remember that this is the symbol for divisible. Then, so implication, n itself must have been divisible by 4. So that's the theorem statement, and you can imagine that this right here is like your p of n. So you have to find an n such that this is false. Okay? That is the idea, and it's an implication, and you know your implication truth table. So give that a shot. Try and find an n such that this is false. Okay? And remember to go back and look at the definition of divisible. If you don't know where to start, it's usually very useful to go back to the definition of all the things that are in your proof. Okay? All the things that you're assuming. So x divides y means that y equals k times x. Okay? For some k that such that x is not equal to 0. Okay, so all that stuff, remember that stuff, and give this a shot now. Okay, so assuming that you have tried it yourself, so we need to find an n, and there's an art to this. You just have to try a bunch of options, usually. Try p of 1, try p of 2, etc. So this is false because there exists an n such that this is not true. And here's my n, okay? N equals 2 does not work. Okay, now let's see why. It doesn't work because it's an integer. So that's true. And it is n squared is divisible by 4. N squared is divisible by 4 because that's saying that 4 is divisible by 4. Because 4 equals 1 times 4. That can be our k. Yeah? So by definition, that's totally fine. But, and this is why it's false, because the one way to make an implication false is for this side to be true and this side to be false. Okay, so that's what you should have been trying to accomplish. So this side, make this true somehow, and then make this false. That's how you make the whole thing false. Okay? Now is the kicker, because n is not itself divisible by 4, and we say that by writing a slash through this. N is not divisible by 4 because, remember that n is 2, because 2 is not equal to some number k times 4, where k, we have some requirements for k. It must be an integer. You see that? Okay? For any integer k. Because if you use math, you notice that k must have been 1/2. Yeah? That's the idea. So this is our counterexample, and it's 2. Maybe I should put a box around that or something. So that is, you just got to find me a counterexample if I ask you to do this on your homework. And you can reason like this. It's like, okay, the reason that it's false is this and that. All right? So hopefully that's not too bad. We're going to keep trucking now. We've talked about how to prove for all. We've had some examples now, or disprove for all. Now let's prove there exists, or disprove there exists. So remember how to do that. You just need to find some element in the domain such that p of that element, if you're trying to prove for all, there exists an x such that p of x is true. Okay, so you just got to find some a such that p of a is true, and a exists in the domain. Oops, we don't know that symbol yet. A is in the domain. And p of a, then you have proven there exists an x. Yeah, there exists an x such that p of x is true. All right, so that's how you can do it. And in English, again, you only need to find one good element where the domain is in the domain, where that conclusion is true. So just find one a, and then you've suddenly shown that, yeah, there is something in the domain such that p of x is true, if we call it that thing x. Now, on the flip side, to disprove an existential statement, you have to do a lot of work because you suddenly have to prove a for all. Remember that not, if you're trying to prove that it's not true that there exists an x such that p of x is true, oh man, that means that's equivalent to for all, right? For all x, it must be the case that it's not true for any of them. All right? So in English, my best way of translating this is, okay, it's not true that there's one element in the domain, at least one element in the domain such that p of x is true, which means that for all of those elements in the domain, p of x must be false. Okay, that's how I read that. So this is the English way of saying that, and that is your recap on proving a there exists or disproving a there exists. And now it is your turn. Okay, so prove the following statement, where n1 and n2, they need to range over integers. That is their domain. Okay, so give that a shot, and let's come back here. So hopefully you didn't have any trouble finding your n1 and n2. So all you have to do to prove a there exists statement, you get to find values of n1 and n2 such that this holds. Okay? So this is how we prove it. So let n1 equal, I don't know, 7, and let n2 equal, I don't know, -2. Then n1 plus n2 equals 5 QED. Yeah? So you can pick plenty of n1 and n2s. There exists says nothing about there being multiple answers. We just found one of them, okay? And I'm sure you found a different one, okay? So that is a nice proof. It's not too hard to prove there exists, assuming you know your domain well. Okay, let's keep on going. Okay, so let's go ahead and give this one a shot. All you need to do is state what needs to be proven in order to show that the existential statement below is false. So you don't actually have to prove it. Just show me what you would need to go and prove to disprove this statement. Okay, so hopefully that makes sense. Give that a shot, and we'll come back and do it ourselves. So this is one of those that you can probably do in English. Okay, so there exists a negative integer that is equal to its square. So the opposite of that, to show that it's false, it's like, okay, for every negative integer it must not be equal to its square. I is not equal to I squared. And if you didn't know that you could say something like this, if that process, if that jump doesn't make sense to you, you can be very methodical about it, okay? And here's how you can do it. So this is equivalent, this first thing is equivalent to, and we're trying to negate it, remember? It's equivalent to negating there exists a negative integer, let's call it I. So there exists an I, it's negative, so I is less than 0. And it's equal to its square. And I equals I squared. Okay, so we want to convert this somehow to English. Technically you can just say it's not true that there exists, but I think that that is not the point of this question. Okay, so this is equivalent to, if we push this inwards, flipping this from an exist to a for all, and then negating the inside here. For all I, it's not true that I is less than 0, and I equals I squared. And we can keep going, could bring this in with De Morgan's rules. So it's not true that for all I, So we can negate the I is less than 0 part, and this and gets flipped to an or, and we can negate the I equals I squared, which becomes I is not equal to I squared. And I didn't flip this one. I kept this negation for a reason, because this is a not something or a something else, which is equivalent to an implication. For all I, did you see that? I is less than 0 implies that I is not equal to I squared. And this is, in fact, this English statement. Right here. So for all I, if I is negative, then I is not equal to I squared. Okay? So equivalently, you can say it like this. So you see how you can be very methodical about it. Just look for patterns, and you can eventually convert it to something nice. So be on the lookout for implications. That's usually useful. Okay? So hopefully it's all coming together, and you're making great leaps in your proof abilities. So the next thing that I want to teach you is how to prove a conditional statement, because these will be everywhere. They will always come up. You will always be proving things like this, because you're always going to make some kind of assumption, usually. Okay? I can actually use it on one of the things that we just had an example of, one of our questions. I think I remember an implication. So the idea is, in order to prove, it's called a direct proof, to prove something that looks like P implies Q, what you do is you assume the hypothesis, and then you prove the conclusion. And so it looks something like this. So assume P, and then therefore Q, or sorry, assume P, then like somehow prove Q, and then suddenly you have with both of those together, P implies Q. Okay, so let me show you why this is all valid, why it actually works. So let's go back to the truth table for P implies Q. And I'll show you why it makes sense to assume the hypothesis and then prove the conclusion. Oops. False, false. So it's true, false, true, true, right? And the idea is you get to assume that the hypothesis is true and then go and prove your conclusion. Why do we get to do that? Why is that a valid way of proving a implication? So the idea is there's only one way for your proof to be wrong, for an implication to not be true, okay? And it's this one way. As long as we make sure that this is not the case, we are golden, okay? So, for example, if your hypothesis starts out false, the implication is always true, okay? So we don't have to worry about that. So if P is false, hey, we get a free lunch, we get P implies Q automatically. So these are the two cases that are interesting, because P can be true, but it's also possible to ruin everything still. Okay? So all we have to do to prove P implies Q is to show we're not in this case. Okay? That's the one thing, that's all we have to do. We want to prove truth, true things. So all we have to do is prove that we're not in this case, this one bad case. Just show we're not there. And the way you do that is by assuming that P is true, because that's one way that this could go wrong. Okay, P is true. We need to show that Q is true and not false. Okay? Because if we show that it's true, we know we're in this case and we're golden. Okay? And if P just so happened to be false, we got it for free anyways. Okay? Hopefully you followed me there. But that's the idea. We get to assume that P is true and then show that Q is true, and then we have made sure that we're not in this case. Okay? So that is how I want to show you that. And hopefully that made sense. Please yell at me in office hours if it didn't, because this is key. Okay? We just need to show that we're not in this one case. And so if we assume that P is true, just need to show that Q is true to make sure that we're in the good one. All right. So we're going to get plenty of examples for these. Lots and lots of practice. Okay, so prove the following statement using a direct proof. So if x is an even integer, then -1 to the power of x is equal to 1. Ooh, this is interesting. How fun. Okay, so what's P and what's Q? Okay, so let's see here. We have an if-then, so we totally have an implication. So what's P and what's Q? I think that is an even integer. X is an even integer, is our P. And the then is the implication. And here is our Q. Okay, do you see that? I hope you do. And so what we get to do now is assume this and prove that. And then there's a secret for all going on as well, because X is arbitrary. It's just an arbitrary even integer. Okay, so assume this P, prove this Q. Are you ready? So we say proof. And then we get started. So the first thing we do is say what we're going to do. So assume x is an even integer. And it's our job to show that -1 to the power of x is equal to 1. Are you ready? So we're going to use this, use some definitions, and we're also going to use some just algebra concepts to prove this. So when in doubt, go to the definitions of things. So even is one of our definitions that we gave up here. So let's go there. So an integer is even if there exists an integer k such that x equals 2 to the k. So we get that for free. Let's just use the definition. So x equals 2 to the k for some integer k. Int k. So now we have this as well. That's part of our arsenal to go and prove this final statement. Okay? And now we're ready, I think. So -1 to the power of x using this equals -1 to the power of 2k. Using some math, that's -1 squared to the k. Using some more math, that is, well, -1 squared is just 1, right? Equals 1 to the k. And finally, that equals 1. And this was one side of q, and this was the other side of q. QED. Okay, did you follow that? That's very important. So we essentially just proved this statement for all x. X is even implies that -1 to the x equals 1. Oops, my computer is going very slow for some reason. There it goes. Hopefully you still hear me. So we proved this, and it was kind of taken for granted that we had a for all here. So x was arbitrary to begin with, and so we definitely proved a for all. We didn't even have to say it. Okay, so we just went straight to this implication, and that is exactly what you can do. Get rid of your quantified thing by, in this case, finding an arbitrary element, we'll call it x, and then prove the rest of this, which happens to be an implication, and so we used direct proof. We assumed the hypothesis and proved the conclusion. Okay? Isn't this fun? It's really fun to just find these patterns. It's like, okay, yes, I totally proved this beyond a shadow of a doubt. Okay? It's all beautiful and wonderful. Math is an art. Okay? If you didn't think to use the definition of even, don't worry. This is stuff that you build up over time. Okay? And that's why I'm going to force you to do several examples and then also do your homework. So I want you to now try this one using the secrets that I have showed you from the previous example. So give this a shot. The sum of an odd and an even integer is odd. So give that a try. Coming back, let's do this. So the sum of an odd and an even integer is odd. Okay, what in the world does that mean? Why is there an implication? So we need to convert this to math. Okay, maybe that's useful for us. So there is, this statement talks about two integers, an odd one and an even one. So I think we have some variables. We have like an x and we have a y. We know that x is even and y is, oh sorry, let's say x is odd, because that was the first thing. Let's just say that x is the odd one and y is the even one. Okay? And y is even. And we want the sum of them to be odd. And now I think you can find the implication in this. X plus y is odd. Okay, so there's that. And these are for all quantified. Okay, so it does take practice to go from this English to this math, but you're going to do it so much that it'll eventually become second nature. So I hope you see where the implication is coming from now. Okay? So if you have these facts, then this fact must also be true. That's what this sentence is trying to say. So let's assume, well, proof. Assume x and y, assume x is an odd integer and y is an even integer. Okay? Assume x is odd and y is even. So assume your hypothesis, prove your conclusion. And we're keeping x and y arbitrary so that we get our for alls out of the deal. Okay? So we're looking at this now. We've assumed this, and now it's our job. All we have to do is show that this is true. Okay, so how in the world are we going to do that, you might ask? And the answer is to go back to the definition. So if you didn't try that yet, and you didn't get it to work, use these definitions right now. Try it yourself again, and then see if you get it this time. Okay, so let's do it. So if x is odd, so let's see, x equals 2k plus 1 for some integer k. And y, Well, y is even. It's 2 times some other k. It's not the same k. That's not right. It's some different thing. Okay? Y equals 2 to the... what comes after k? L, that's hard to look at. It looks like a 1. M. Y equals 2m for some integer n. So now, all we have to show is that x plus y is odd. And we can use the definition as well. So what we need to show to prove this theorem is that x plus y equals 2 to the, I don't know, r plus 1 for some r. You see that? So unfolding the definitions gives us some stuff to work with. Okay, so this is what we still need to do. We know this, we know this. Can we use those facts now is the question. Okay, x plus y, we need to show that it's odd. So x plus y equals 2 to the k plus 1 plus 2 to the m, just by unfolding our definitions of odd and even. Can we use that now? Can we use this to show that x plus y is odd? Okay, okay, we can do it, because we can bring the m's and the k's together. Equals 2 to the k plus 2 to the m plus 1 by math. And now we can take a 2 out. You see that? That's the secret. That equals 2 to the k plus m plus 1. And so if we use this number right here, as our r, we've suddenly proven oddness. Okay? So therefore, x plus y is odd, by definition. Okay, and that was what we wanted to prove. So QED, mic drop. Did you see that? Okay, it kind of happened fast, but all we had to do was unfold these definitions, and suddenly we had a proof going. So I hope you were able to get that. If not, don't worry. Plenty of practice is coming up still. Okay? So let's just take stock of what we did to prove this statement, because a lot of things had to happen simultaneously. We had to go from this English to suddenly figure out, okay, I want to use a direct proof, so there better be an implication somewhere. Let's convert it to math so we can see that concretely, and then let's go and prove these things. We're proving for all statements, so we need to assume that we have arbitrary elements that exist in the world, and then we have to prove the rest of this statement using those arbitrary elements. And we're going to use a direct proof because it's an implication. So we're going to assume that this is true, so assume that x is odd and y is even. And we're going to show that x plus y is odd. Okay, and the way we got there was by unfolding definitions and then folding them back up. So, yeah, that was fun. Okay, it's like a little scavenger hunt. All right, so let's go to a next one. So again, I want you to try this yourself first. This is how you learn. I have to force you to do things. Okay? If we were in class, I'd force you to do it with a group partner or something, and that would make it slightly more fun. So I'm sorry you're probably watching this alone right now, but it's very good practice, I promise. Okay. So I want you to prove this statement using a direct proof again. So for any positive real numbers, x and y, x plus y is greater than or equal to the square root of x times y. Okay? So give that a shot. You might want to convert it to math. Maybe you want to go straight to the proof, and you can see the math already without actually writing it. Okay? So, assuming you gave it a shot, let's do it ourselves. So, again, I'm going to translate this to math just to get us started. Until you can see it, I'm going to do this. Okay? So for any positive real numbers, x and y, so for all x and for all y, they're both positive. So x is greater than 0 and y is greater than 0. For all of those things, if all this is true, then this is true. Do you see the hidden then? So all that implies x plus y is greater than or equal to the square root of x times y. See that? Okay, so there is our proof. So assume x and y are arbitrary, assume this, prove that. That's what you got to do. And maybe I should write that just for posterity's sake. So assume arbitrary x and y. Assume this. Prove this. That is the game plan. Okay? So let me give the way that I would prove it. So proof. Okay, assume x and y are positive numbers. And a real number is just something that can be have decimals. Okay, 3.14 is fine. So decimals are okay. Okay, so assume that x and y are positive numbers. We need to show now that this is true. Okay, to show x plus y is greater than or equal to square root of xy, and then we will have proven the proof, the entire theorem, if we can just show this. Okay, well, let's do this. All right, so we need to do this on two fronts, it seems. So how do we get started? There's going to be some math trick involved usually, but that is everything that we have to begin with. Okay, so let's think about this for a second and then figure out what the secret is. Okay, I admit I had to look up to make sure that what I was about to say was correct, because I thought I had a way, but it seemed too complicated. But it seems like that's the only way to go. So I can get to here, I noticed, by if I had x plus y squared greater than, or equal to, I guess, greater than, still fine, greater than xy. If I squared both sides, I can go to here, and I kind of want to come from there is the idea. Okay, so because then I could put like, I could expand this out. It's like, okay, then I could come from x squared plus 2xy plus y squared greater than xy. And I can come also there from x squared plus xy plus y squared greater than 0. Okay, that is the idea. So I could go from here to here to here to there by taking square roots at the very end. Okay, so that's essentially the proof. And I thought there was a secret, but no, it's just kind of complicated, sorry. But that's why we're doing it in class. So hats off to you if you discovered this fact. I got here and was like, there has to be an easier way. But no, there was not. Okay, so here's what we can do. So if we assume that x and y are positive, we have these facts immediately, okay? X is greater than 0, y is greater than 0, of course. That's what it means to be positive. But you can multiply both sides of this by x to get x squared is greater than 0. Same for y squared is greater than 0. And you can multiply this one by y to get xy greater than 0. So by math, we get all these things. And then, if you add all this kind of stuff together, you suddenly have things that are still greater than 0. Okay, that's how math works. So, dun dun dun. Let's see here. Y squared greater than 0. So we have these facts. Okay, this is what we know. We can get for free from math. So now I'm going to build up. Okay, this thing up here. So first, x squared plus xy plus y squared is greater than 0. We get that because of these things. Okay? I hope you can see that. Okay, and you can get that because if you add two inequalities, it becomes the same thing. So it's like x squared plus y squared greater than 0 on both sides. Okay, hopefully that's all making sense, that algebra is coming back to you. So we know this, okay? And then we kind of have to translate this to some kind of English, but I'm going to leave that to the reader. So this becomes now, how do I want to say this? We can turn that into, by math, I guess, going the other way. We can add an xy on both sides. Dun dun dun. So we get x squared plus 2xy plus y squared, and that is greater than 0. Oh, sorry, greater than xy, because we just added xy to both sides. Silly me. Then we can go from that to actually get squareds on the left side. We can get x squared, x plus y squared. That's one thing that we needed. And then we have that is greater than xy still. And then we can go from that to, by taking square roots, x plus y is greater than xy. And all we needed to show was this, which the only difference is the equal sign. And if you have something that's greater than, yeah, it's totally greater than or equal to as well. Okay, so that was a bit of a hair puller, but it just goes to show that math laws are important to know. So that is the proof of this statement. If you got that, again, hats off to you. That's a bit of a difficult one. Okay, moving right along, let's prove this statement using a direct proof. The average of two odd numbers is an integer. So you can't accidentally get a 1/2 in there somehow, is the idea there. So give this a shot. As usual, I will come back and do it after you have tried. Okay, so let's first convert this to math. I'll write it up here just in case I run out of room again. This is saying something like, okay, the average of two odd numbers, so we have a for all, again, we have two numbers for all quantified over, x and y. We know that they're both odd, so x is odd and y is odd, and apparently the average of those two numbers is an integer, we're trying to say. So that if this is true, you see the secret then again, if they're both odd, then their average must be an integer. So x plus y over 2 is an int. Okay, so this is what we need to prove now. So assume that x and y are arbitrary, assume that this is true about them, and then prove this. Okay. Proof. So let x and y be odd numbers. Okay. By the definition of odd, we usually need to use that, so let's just use it now. So x equals 2 to the k plus 1, and y equals 2 to the m plus 1 for ints k and m. Okay, now all we have to show is that their average is an integer. So let's try and get their average using these new values for x and y. So x plus y over 2 equals, okay, 2 to the k plus 1 plus 2 to the m plus 1, because x is 2 to the k plus 1 and y is 2 to the m plus 1, so just add them together, over 2. And I think you see that this is going to end up working out in our favor, because we can bring the 2's together and add the 1's. Equals 2 to the k plus 2 to the m plus 1, no, sorry, plus 2. Got rid of a 1 somehow. Over 2. Oh man, is that equal to k plus m plus 2? K plus m plus 2 is an integer because k and m are integers. Because k and m are both ints. You add integers to integers, you still get integers back. Okay? So, k to the m plus 2 equals x plus y over 2, and that was all we needed to show. Dun dun dun. That's the proof. Maybe we should say at the very end, therefore, x plus y over 2 is an int, just to drive the point home. Okay, then mic drop, and we're done. Okay, did you get that one? It's a lot easier than the previous one because we didn't have to think of any secret tricks, but that is that. Okay, so let us move on to the next topic, the next way of proving things, and we'll go from there. So you can actually prove things by what's called the contrapositive. So you remember that the definition of the contrapositive is you have an implication, and then you swap stuff, and you add knots on both sides. So they're actually equivalent. These two things are equivalent. So you could just as easily prove this one, and you get this one for free. Okay, so you can prove either one because they are equivalent. So let's just remind ourselves why they're equivalent using a truth table. Let's see here. So the truth table is probably the harder way. I'll show you a very easy way to prove this using our equivalence rules. Okay, so P implies Q and not Q implies not P. So let me make our truth table for that. We need P and Q, and P implies Q, and not Q, and not P, and not Q implies not P. Okay, so let's fill all that in. Feel free to fast forward. That's one of the beauties of television, right? So let's do that. So we got true, 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 false, false, true, false, false. P implies Q is true, false, true, true. Not Q is false, true, false, true. Not P is false, false, true, true. And now I can use this with my implication rules to get things. So false implies whatever, it's always true. True implies false, that's the one case where it's false. False implies whatever, so we're good. And then true implies true. Yes, that's the good case where you do have that thing. Okay, so bam, they're equivalent because these all match up. True, false, true, 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 false, true, true. Yeah? So that's one way to notice that, hey, I could just prove this one instead of this one. It's the same thing. Alternatively, we can prove that they're equivalent using our equivalence rule. So remember that P implies Q is equivalent to not P or Q. That's quite nice. Let's come at it from the other side over here. Let's say that not Q implies not P. Well, negate this or this. Not Q or not P. Ooh, two nots is a true. They go away. Dun dun dun. Q or not P. And of course, you can put anything on either side of the or, it doesn't matter. So that is the same as that. Wasn't that fun how they met in the middle like that? So that is, that's the beauty of proofs. All right, so maybe you should try this one, and we're going to stop for the day. So I'll come back and we'll prove it together, but I want you to think about this one in between lectures, okay? So I'll see you in the next lecture and we'll go over the answer, but do give this one a try.